Howdy Pima Aztecs. Welcome to Module 1B. So Module 1A talked about sort of general concepts of anatomy and physiology, and it was dealt with Chapter 1. This is a little tricky. Module 1A dealt with Chapter 1. Module 1B deals with the first part of chemistry, and then Module 2A and 2B will deal with the second parts of biochemistry. It'll still be Chapter 2. So I hope I thoroughly confused you on that. Let's take a look at this. So did you ever look in the chemistry room in high school or even here at Pima and see this amazing Mendeleev's periodic table of elements? That's what this is. I remember the first time I saw it in high school, I was like, or maybe junior high, I thought, that is the coolest thing. What does it all mean? And then I found out. So let's take a look. There's a lot of different colors on here. Couple basic things that you should memorize and never forget. If you're looking vertically, these guys are called columns. And if you look horizontally, so this way, if you look horizontally across the periodic table of elements, those are called rows. So you should remember columns. So for example, column 1A, column 2A, column 3B, etc. go vertically. Rows go horizontally. All right, that's the number one thing to note. And then it gives you all these different colors. And for this class, we're not going to study the difference between an alkali and an alkaline metal, but it shows you the metals and all their colors. And then it tells you here if that element in the periodic table of elements is a solid, liquid, gas, or if it's a synthetic compound that humans have made. Okay. What else do we want to talk about? Some of the important elements that make us up, us living things up, probably already know this, would be carbon, hydrogen. What about our old buddy oxygen? And I think it's like 70-some% of the atmosphere is made up of nitrogen. So those are kind of important elements for our study. Other important elements for our study would be sodium, potassium. Those are really important atoms in the nervous system. So sending signals in the nervous system. Sodium and potassium are really important. You probably know that you should eat a lot of calcium. That's good for you. Magnesium is good. You put fluorine or fluoride, sorry, it's fluorine on the periodic table, but it's fluoride in your toothpaste. And then you probably know this, sodium and chloride ion make up sodium chloride. That's table salt. And you've probably heard of neon signs. There's neon. Nickel, that's my favorite coin, is the nickel. Here's copper, zinc. So anyway, that's kind of a basic overview of the periodic table. And then we'll talk about what these little numbers mean over the top of the element name and down here on the bottom of the element name. But before we get into that, let's start with a little bit of physics, because that's where you should always start. I always argued in high school that you should teach physics first, then chemistry, then physiology. And they usually save physics for your senior year, which didn't make any sense, because physics, that's the basis of physiology. So you should study physics to really understand physiology. But here's a little bit on anatomy and physiology. physics, you probably learned this in grade school, I think. The definition of matter. Matter is anything that occupies space and has mass or weight. So mass, for example, your mass wouldn't change if you were on Earth or Mars or the moon. Your mass would stay the same, but your weight would change because weight has to do with the pull of gravity on your mass. Matter exists as one of three states. This is probably the part you learned as a little kid. Matter can be a solid, and a solid holds its shape. So for example, this rectangle holds its shape and it has a fixed volume. So whatever the volume of this is, it's fixed. Matter can be liquid, and liquid takes the shape of the container. It doesn't hold its own shape. A liquid takes the shape of the container, but it does have a fixed volume. So whatever this is, 20 milliliters, it has a fixed volume. Gas, on the other hand, not only takes the shape of the container, but it takes the volume of the container, because each one of these little blue dots is a gas molecule, and they're, moving around inside this container. Okay, so matter and energy, really important in physics. Matter has three states, and matter can be changed physically. So, for example, in this cartoon, when water, take some water, this glass of water, you put it in an ice cube tray, makes ice. You got a physical change, right? There's no chemical change. This water in the ice and the water in the glass, everybody knows, is H2O. So that doesn't change chemically. It's a physical change. Matter can, however, be changed chemically. And a chemical change would alter the chemical composition of a substance. So for example, why you should keep your hydrogen peroxide lid on really tight and in a brown bottle, because over time hydrogen peroxide will chemically change into water. So here's hydrogen peroxide, H2O2. So here's the two oxygen atoms, and here's two hydrogen atoms. H2O2 changes into water, H2O. And then you also have chemical changes when you digest food. So here you are, you're ingesting your delicious meal. And then when you digest the food, you're chemically breaking the glucose down. You're chemically breaking your protein or your fat down. It's a chemical change so that you can get it across the wall of your intestine into your blood. All right. Shown is God right here. Found this. I was looking for a fun cartoon of carbon, hydrogen, oxygen, and nitrogen, and I found this. Shown is God. So matter. We've said matter can change chemically and physically. We've said matter has three states. We've said the definition of matter is anything that takes up space and has mass. But what is matter made of? Matter is made of elements. Where do we find elements? The periodic table of elements. So elements then are the fundamental units of matter. So for example, hydrogen peroxide, the elements that are the fundamental units of matter, hydrogen peroxide, would be hydrogen and oxygen. 96% of your body weight, a human body weight, is made of the four elements, C-H-O-N, chon. And your periodic table of elements gives a complete listing of all the elements that we found on Earth and that have been made by scientists. Here's some tables from your book. It says common elements making up the human body. So it just gives you the element is oxygen. The atomic symbol is O. Percent of your body mass, 65%. And what's the role of oxygen? It's a major component of organic and inorganic molecules. So for example, glucose, C6H12O6, 6 oxygen molecules. And then it helps you make ATP. Carbon is C, it's 18.5% of your body mass. Hydrogen is H, is 9.5% of your body mass. And nitrogen is N, and it's 3.2% of your body mass. Nitrogen is really an important component of proteins and nucleic acids. So nucleic acids, that's RNA and DNA. And then here's some lesser elements, the lesser gods. Even more lesser gods. Remember sodium and chlorine, or sodium chloride, the ions, when they're in ionic form, make up sodium chloride, or delicious table salt. Okay, still on physics part of this video. Physics, matter, has to do with matter and energy. I will talk about energy. So the definition of energy is the ability to do work. So I always find this interesting. They don't have a, in my opinion, it's not really a true definition of energy. It's just telling you what energy can do. It's not telling you what energy is. It's really hard to explain. But anyway, the definition of energy is the ability to do work. And then we see these cartoons down here for kinetic energy and potential energy. You've probably heard of those too, if you took physical science in high school. Kinetic energy is when energy is moving. So if energy's in the system or energy's out of the system, it's kinetic energy because it's moving. So this guy's moving up the hill, so he's using kinetic energy, and now he's moving down the hill. So that's kinetic energy as well. And then at the top, right here where he pauses for just a moment, that's potential energy. And then here's this cartoon shows this girl with the ball. The ball has a lot of potential energy. It has the potential to do work, but it's not doing any work. But when she lets it go, potential energy is transformed into kinetic energy because the ball is doing work on the atmosphere. So this is why energy is difficult to define. Energy has no mass. Energy does not take up space. So that's kind of weird. Like matter has mass, takes up space. Energy, no mass, does not take up space. So energy is not matter. And there's two general forms of energy. We talked about those, kinetic energy and potential energy. I like to think of potential energy sometimes like the Hoover Dam. So you've got the dam, you've got all that water behind the dam, and if the dam is shut off, there's no water going over the dam. But then when you open the dam, the floodgates, and then the water starts moving, that changes from potential to kinetic energy. We can only measure energy by its effects on matter. Can't measure energy any other way. It's difficult to define. Energy can change form. You've probably heard that energy can change form. So here's some specific forms of energy. Oh, but let's look down here first. The first law of thermodynamics. It's also called the law of conservation of energy. It says energy can neither be created nor destroyed. You may have heard of that. Energy can only be transformed or changed from one form to another. And then it shows in this cartoon the energy transformation. So I don't know if this is the best thing to eat before you go on a bike race or whatever you're doing over here. But chemical energy, so it's delicious ice cream cone. There's fat and sugar. And all that fat and sugar is held together. For example, glucose is held together by chemical bonds, and the bonds change form, and you change the chemical energy into ATP, and then ATP can be used to do mechanical energies, or used as mechanical energy to ride your bike. Radiant energy from the sun comes down, allows trees to change that radiant energy into chemical energy. That's photosynthesis. Here's some gasoline. So what is that? Octane. Put that in your car, and your car moves changes from chemical to mechanical. And then electrical energy, so you plug in your lights, or you plug in your plug to your, looks like an oven, changes electrical to thermal energy. And then your book doesn't count thermal energy as a type of energy. Well, Marieb doesn't, but it can be. Thermal can be a type of energy. So specific forms of energy, chemical energy. Energy is stored in chemical bonds. So for example, glucose, C6H12O6, it's held together by chemical bonds. Another specific form of energy, electrical energy. That's energy resulting from movement of charged particles like electrons in atoms that we'll talk about later. And then mechanical energy is specifically or directly involved in moving matter. So the matter would be this car, taking up space and having mass. Mechanical energy moves it. And then radiant energy travels in waves, so light waves. And then there's particles in those light waves called photons. Okay, let's take a look at this. Here's some serious looking chemistry. So adenosine triphosphate, my old friend ATP, that's your energy in the cell. So ATP, the TP stands for triphosphate. 1, 2, 3 phosphates, and between those phosphates are really high energy bonds. So when you break those bonds, energy is released. And then here's adenine. So this is the base, adenine, and then the sugar it's attached to is ribose. So the whole thing is called adenosine triphosphate. If you need energy, so here's energy over here. If you need that, you hydrolyze ATP. So that means you take a molecule of water. So here's ATP. You take a water molecule and you break that terminal phosphate bond, and then that phosphate comes over here and energy is released. And you go from being ATP to ADP, adenosine triphosphate, to adenosine diphosphate. Okay, so ATP is the energy molecule in the cell. And we'll talk a whole bunch about ATP in 201, 202, 205, 218. So you should get to know ATP. What ATP does is it traps the chemical energy of food in its bonds, so these high energy phosphate bonds, and releases the energy to do any work that the cell needs done. So they say ATP is like the currency of the cell. So if you want to build something in a cell, you got to have some currency, you got to pay to get things done. The way you pay is with ATP. Okay. We said that matter is made of elements, so that means elements are the fundamental building blocks of matter. Then logically, if elements are made of atoms, then you could say atoms are the fundamental building blocks of elements. And then you could say atoms are made of subatomic particles, and those subatomic particles are the fundamental building blocks of atoms. And then you could say subatomic particles are made of, I don't know, muons and bosons. And you could keep getting smaller and smaller. But we'll stop here. Matter is made of elements. Elements are the fundamental building blocks of matter. And atoms are the fundamental building blocks of elements. Atoms of one element differs from the atoms of the other elements. So for example, lithium atoms are built differently than beryllium atoms. Gold atoms are different than arsenic atoms. So here's arsenic, and where's gold is Au because it's Latin for, there it is, aurum. Aurum is Latin for gold, so there's gold. And so every atom has an atomic symbol. So for example, Au, like I said, is aurum, and well, aurum in Latin is gold. and then arsenic symbol is As. Okay, so those are the elements, but what about those, and every element is made up of a certain kind of atom. But what are atoms made of? Atoms are made of subatomic particles, and we'll just look at the ones that are important for anatomy and physiology. We won't go in too much depth. You've probably seen this before. This is a planetary model for an atom. So you have this thing in the middle called the nucleus, and the nucleus contains positive protons, neutral neutrons, and then around the nucleus in this orbit or orbital, you have the negative electrons. So P with the plus sign, that's positive proton. It's the red guys. And N with a 0, a superscript 0, means there's neither a positive nor a negative charge. Those are the yellow neutrons. And then the electrons are negative, and they orbit around the nucleus. Okay. Protons are positively charged, like I just said, but what's their mass? They have a mass, and it's such a tiny particle, so they call it they say that protons have an atomic mass, because this is an atom, right? So they have an atomic mass of 1 atomic mass unit, or 1 AMU. That's the mass of a proton. Neutrons, don't get these mixed up. Neutrons are uncharged, they're neutral, but they also have a mass of 1 atomic mass unit. So these protons and neutrons in the nucleus, they have a mass, and it's 1. They also have a charge, and protons are positive, neutrons, well, actually neutrons are uncharged. And then the electrons are the other subatomic particle that has a charge, and they're negative. And they virtually have no mass. But it's like 1/2000th of an AMU. It's really small. So for our purposes, because we're not physicists, we'll just say that electrons virtually have no mass. Okay. So remember the atomic mass. Now this gets tricky because it's different in different books, but in Marieb, I think they call the atomic mass, they call it the mass number. So atomic mass or mass number refers to a single proton, single positive proton, which has an atomic mass of 1 AMU, or a single neutron, which has an atomic mass of 1 AMU, or the whole atom could also have an atomic mass. So for example, with the helium atom that we've been looking at, what do you think the atomic mass of the helium atom is? Well, if each one of the protons has an atomic mass of 1, and each one of the neutrons has an atomic mass of 1, and there's 2 protons and 2 neutrons, and remember, electrons we don't really say have a mass, the helium atom would have an atomic mass of 4, and you usually have to put units on that, you know, like miles per hour. You got to have units. The units would be AMUs, so the atomic mass of the helium atom would be 4 AMUs. Atoms themselves are electrically neutral. So you can see, here's how that happens. So remember the neutrons, they don't have any charge on them, so they're not going to cause any electrical phenomenon. The protons are positive, and there's 2 protons, they each have 1 positive charge, but look, there's 2 electrons, and they each have 1 negative charge. So 2 positives plus 2 negatives makes the atom neutral. So atoms are neutral, but atoms can form ions, which are not neutral. Ions are electrically charged atoms. They've lost or gained electrons. So let's say you have the sodium atom is just Na, but if you add a, well, if you take away a negative charge, it becomes positive. So it'd be a sodium ion. So if this were sodium, this helium were sodium, it's not. If you take away one of those electrons, that means this is going to be, the whole atom is going to become one charge more positive. If you are a positive ion, you're called a cation. So for example, sodium plus, and there should be a 1 there. They just never write it. If it's greater than 1, they'll put the number. So if this were Na plus 2, they'd put the number 2. But because it's Na plus 1, they just don't write 1. They just expect you to know that. So positive ions are cations. So this would technically, it would be a sodium ion, but even more specifically, it would be the sodium cation. And then if you're a negative ion, you are an anion. Okay, so this just shows different models. You can, we've been working with this guy, the planetary model, but there's a kind of a better model for an atom called the orbital model. Basically, it has the same components. It's got a nucleus with protons and neutrons in it, but then the electrons are not in these specific shells like they are over here. See how that electron, you can find it in this shell. It's kind of fuzzy. Like the electron could be in any one of a number of different orbitals, and it gets really complicated. If you've had this in chemistry before, you know what I'm talking about. But we'll probably just keep it simple. Okay, now let's look at some different atoms. So here's the hydrogen atom. How did I know to call it the hydrogen atom and not the hydrogen ion? Because if you look in the nucleus, it's got one positive proton, that's one positive charge, and it's got one negative electron, one positive and one negative charge that cancel each other out. That means this is the hydrogen atom because it doesn't have a charge on it. Check it out, helium. So there's two positive protons. Remember, the protons are red. Two positive protons. There's two neutral neutrons, so they don't really count. And then there's two negative electrons. So two positive protons, it's two plus charges, two negative electrons, it's two negative charges. Two positive charges, two negative charges, they cancel each other out. That's the helium atom. Okay, let's check out lithium. So here's lithium. It's got three positive protons, and then remember the neutrons. Here's the neutrons, they don't really count. Three positive protons and three negative electrons. Three pluses and three minuses they cancel each other out, so that's a lithium atom. Couple other things to point out. What would be the atomic mass of the hydrogen atom? This is tricky because look, there's a 0 in front of the N. Might make you think it has a 0 mass, but in this, sorry, I meant to say this 0 up here makes it tricky. You might think it's a 0 mass, but the 0 in front of the neutron means there's no neutrons. So if there's no neutrons, they don't contribute to the atomic mass. There's one proton. Remember, protons have an atomic mass of 1 atomic mass unit. So the hydrogen atom itself would weigh 1 atomic mass unit. So let's look at helium. This is what I should have used. What happened to my little pen? There we go. So there's two positive protons. So two positive protons, that would be 2 AMUs. It's hard to write with the mouse. 2 AMUs plus, now we've got a 2 in front of the neutrons. So that's 2 neutrons, 1 AMU apiece. So that's 2 more AMUs for the neutrons. And then there's 2 electrons, but remember, they don't really, we're not counting them. We're not saying they have a mass. So the atomic mass of this helium atom, 2 plus 2 is 4. Now, lithium, 3 positive protons, that's 3 AMUs. 4 neutral neutrons, it's 4 AMUs. 4 plus 3 is 7 AMUs. That's the weight of the lithium atom. And one other thing to point out, when you're putting electrons away, you have to put a certain number in each one of these shells, or kind of call them an orbital loosely. I'll call them a shell or an orbital. So in the first shell that's closest to the nucleus here, you can put in 2 electrons. If you have more than 2 electrons to put away, you have to go to the next shell to put your next electron in the second shell. Okay, now we've been talking about atomic mass, or mass number, is the mass of a single proton or a single neutron, or it's the mass of the entire atom. Now we're going to add, this is going to be a little tricky, and I'll tell you why. Because atomic mass and mass number are the same thing, at least for anatomy and physiology. Now I'm going to introduce a new word, the atomic number. So check it out. The atomic number has atomic, like in atomic mass, and it's got number, like in mass number. So it gets kind of confusing because the atomic number is something different. The atomic number is the number of protons in an atom. So the atomic number of hydrogen is 1. The atomic number of helium is 2. The atomic number of lithium is 3. And it defines the type of atom you are. So if you go anywhere in the world, if you find an atom and it has 3 protons in it, it's a lithium atom. That's the end of the story. The number of protons you have defines who you are in the world of atoms. But now that it's maybe a little bit clear to you, let's muddle it up again with this concept of an isotope. An isotope. So in this cartoon, it's a cartoon of the isotopes of hydrogen. So here's our typical hydrogen atom, right? There's 1 positive proton, there's no neutrons, and there's 1 electron. So the atomic mass of this hydrogen atom is 1 AMU. Now there's 1 proton in there, that makes it hydrogen. Look over here, deuterium, there's 1 proton, that makes it hydrogen, but it's an isotope of hydrogen because not only does it have the 1 proton, that makes it hydrogen, but what makes it an isotope of hydrogen is this 1 extra neutron. Tritium is also an isotope of hydrogen. And so there's the 1 proton that will make this atom hydrogen no matter what, but it's an isotope of hydrogen because it's got these 2 neutrons. And this is how they write it out. So this deuterium is an isotope of hydrogen, and you've got the letter H and 2 on that. That means it's 2 atomic mass units. This regular hydrogen, it's not an isotope, this hydrogen has a 1 in front of it. That means it has 1 AMU. Deuterium has 1 proton, 1 neutron, so it's got atomic mass of 2 AMUs. And then tritium has the 1 proton, makes it hydrogen, but then it's got these 2 extra neutrons for a total of 3 AMUs, and then you put the 3 here. So if this is the first time you're seeing any of this chemistry, it's kind of bewildering, but that's the way it goes. So isotopes are atoms of the same type, so they're all type hydrogen, but they have different structural variations. And what that means is they have the same number of protons, that makes them hydrogen, but they have different number of neutrons, that's an isotope. And that also means they have different atomic masses, different mass numbers. So isotopes have different masses. So deuterium has a different mass than tritium. Deuterium is 2 atomic mass units, tritium is 3 atomic mass units, but they're both isotopes of hydrogen because they only have the 1 proton. All right, let's make it even more complicated. Now a new word coming in, atomic weight. Atomic weight. This gets tricky, and when you look on the periodic table of elements and you see a number with a decimal on it, that's always the atomic weight, because the atomic weight is the average mass number of all the isotopes in an element. So you get an average. So 1 plus 2 is 3, plus 3 is 6 divided by 2. So the atomic weight of hydrogen, then 6 divided by 3 should be 2. So it's in a, and that's not a decimal number, but most of the atomic weights of the elements on the periodic table of elements are decimal numbers, because it's also a weighted average. And all that means is if in your formula, in your mathematical formula, if tritium made up 99% of hydrogen atoms, tritium in your average formula would weigh more. And I don't want to get into the math of that, just that's what it is. It's a weighted average. It's not a simple average like I just did for you by taking 1 plus 2 plus 3 is 6 and dividing it by 3. That would be that would be the easy way to do an average, right, of the isotopes. But it's not a simple average. It's a weighted average. It takes into account the abundances of the different isotopes. Okay. So this just says calculate the mass numbers of each of the 3 isotopes. So this has the mass number of 1, this has a mass number of 2, this has a mass number of 3. Now this is a different, well, this is the periodic table of elements, but I put this up because look, it shows you the atomic weight here. Remember, that's the weighted average of all the isotopes. And the atomic weight of hydrogen is 1.008. And then here's the symbol, and then here's the atomic number. Remember what that is? That's the number of protons in the atom. So here's a little summary. Found this table. The mass number in this column, and then versus the atomic mass, also called, some people, well, the atomic mass is the atomic weight. So the mass number is the weight of the nucleus of an atom. So remember, the nucleus, the weight of a nucleus of an atom is the number of protons and neutrons. And then the atomic weight is the average weight of an element. And it's actually a weighted average. The mass number doesn't take into existence of isotopes, but the atomic weight does consider the existence of isotopes and their abundance to get the atomic weight. So the atomic number, that's the number of an element. It's the number of protons in an element. That's the atomic number. That's not in this chart over here. The mass number, also called the atomic mass, is the sum of the masses of protons and neutrons in the nucleus of an atom, or it can be the mass of a single proton or a single neutron, and its units are AMUs. And then the atomic weight, we just talked about that. It's a weighted average of all the isotopes of an element. As kind of a general rule for us, because this isn't a chemistry class, the atomic weight of an element, so this column, the atomic weight, is approximately equal or close to equaling the mass number of its most abundant isotope. And we're not going to go look at the elements and their most abundant isotopes. So just know that it's just a rule of thumb. So this is just a table that shows you the elements. Calcium, the symbol is Ca. The atomic number of calcium is 20. Remember, the atomic number is the number of protons. Atomic number. The mass number is the number of protons and neutrons. So let me ask you this. If I give you the symbol, I tell you its atomic number is 20, I tell you its mass number is 40, can you tell me how many neutrons are in it? Yeah, because you know 20 is the number of protons, and the only other particle, subatomic particle that has any weight is a neutron. So 40, which is the sum of protons and neutrons, take away the number of protons, that gives you the number of neutrons, 20. And then its atomic weight, remember that's the weighted average of all the isotopes. And this column tells you the electrons in the valence shell. And that's really important. And we haven't talked about the valence shell, but the valence shell of an atom is just the outermost shell where you can find an electron. So remember, lithium, you put 2 electrons in the first shell, and then you put 1 electron in that second shell. That second shell would be lithium's valence shell. Radioactivity, it doesn't look like there's really any test questions on that, on radioactivity. But most of the isotopes that we talk about are stable. The nucleus does not decay. But if you are a radioisotope, you are unstable, and the nucleus decays, and it actually changes, it can change into another element. And then radioactivity, everybody's heard of radioactivity. It's the process of spontaneous atomic nucleus decay. And this just shows different types of carbon. Here's carbon-12, carbon-13. They're both not radioactive, but carbon-14 is radioactive. Atoms in general, they have a characteristic way of losing an electron, gaining an electron, or sharing their electron when they're interacting with other atoms. And what that does is they want to be stable. So, for example, on the right side of the periodic table, so these guys are all inert. They don't really share electrons. But these guys tend to be electron hogs. So if one of these elements comes near one of these guys over here, they tend to give away their electrons. So these guys tend to give away their electrons. These guys tend to take electrons. They're electron hogs. So they have, the atoms on either side of the periodic table have a characteristic way of gaining or losing their electrons or sharing. Carbon, it turns out, loves to share electrons. It doesn't want to take electrons. It doesn't want to give its electrons away. It wants to share its electrons. And then here's some molecules. We've been talking about this. Here's H2O. So the subscript 2 belongs to the hydrogen. So these two red circles would be hydrogen, and then the blue one would be oxygen. Here's carbon dioxide. So there's no superscript with the carbon. That just means 1. So this guy would be the carbon. And then the superscript 2 goes with oxygen. So there's 2 oxygen molecules here and here. And then methane gas, CH4. So each one of these red balls is a hydrogen. And this yellow one is a carbon. So forces that hold these atoms together in a molecule are called chemical bonds. So it doesn't really show it in this cartoon, but there are chemical bonds between the carbon and the oxygen atoms, for example. So we've been talking about atoms, but if you are a molecule, the definition is 2 or more atoms of the same element or two or more atoms of different elements that are combined chemically. That's called a molecule. So for example, a molecule can be ozone. So it's got 3 oxygen atoms bound together. That's 3 oxygen atoms, fits this description, 2 or more atoms of the same element. So this guy's a molecule. Or you can be 2 or more atoms of different elements. So for example, water, H2O, that's a molecule. This is a little tricky, and it gets kind of sloppy, but if you are 2 or more atoms of different elements combined chemically, you are a compound. So oxygen can be a molecule or a compound. Check that out. Ozone is a molecule because you have to be 2 or more atoms of different elements, and it's the same element. It's all oxygen. Nitrous oxide can be a molecule or a compound. And I'm not really sure how chemists decide whether to call, for example, water a molecule or a compound. I've heard it called both. To make a molecule, use a chemical reaction. So write it out as a molecular formula. So 1 hydrogen atom, I just put in parentheses. You don't write this out in the formula, but I'm just saying it's a hydrogen atom plus another hydrogen atom. And then you put this arrow, and then on the right side of the arrow you put H2. So 2 atoms of hydrogen make 1 hydrogen molecule. It's writing out a chemical reaction, writing the molecular formula. So the reactants are the atoms, and they're on the left side of the arrow. And then the products are the atoms or the elements on the right side of the arrow. So the reactants would be 2 hydrogen atoms, and the product would be 1 hydrogen molecule in this example.